All right, today we talk about points on a circle and the general definition of sine and cosine. Notice that you should be working on project number 5 and also quiz number 4 has just happened. It was today, so hopefully you've got that into me. So let's go ahead and start with the notes. Last class we defined the sine and cosine functions for angles in a right triangle. Today we extend those definitions to apply to any angles, not just the ones that are in a right triangle. We start by studying something called the unit circle. It's a circle of radius 1, hence the word unit. Unit means 1. Centered at the origin. Fill in the blank angles on the unit circle below. I'll do the first few with you. Okay, so here's our what's going to be our new best friend. It's the unit circle. Okay, so what we're going to do is fill in some of the, well, there are a lot of blanks here, and we'll fill them in over the next few classes. But for right now, we just start by filling in the angles. And we see those little degree symbols there. So for example, this angle right here is our 30-degree angle. So let's go ahead and put 30 degrees right there in that blank. And the next angle, so that means that it's 30 degrees from here to here. And the next one we're going to say is this angle, and that's our 45-degree angle. These are going to be all the special angles that we know and love. And then the next angle goes here around to here. Any guesses? Hopefully we've got 60 there. Next one is this angle from here to here. So that's a right angle, that's 90 degrees, and we'll put that up there. This one here, well, let's see, is the 90 that we had plus another 30, right? Because that's the same as this guy. So I think that's 120 out there. 120 degrees. So go ahead and pause the video here and then come back once you've filled in all of the angles around this circle. Okay, so I've left just 2 that are blank. On the one hand, this is a 360-degree angle here because we've gone all the way around. But you could also think of that angle as not having rotated at all, which would make it 0 degrees. So it's got 2 different names. In fact, all of the angles here have 2 different names. In fact, all the angles here have a lot of names. But for right now, maybe pause the video and just double check that your answers match up with mine. Okay, and once we've got that done, we'll move to the next page. We should also be able to locate special angles that aren't between 0 degrees and 360 degrees. Find the following angles on your unit circle. So 540. All right, 540 is a big angle. I say big because it's more than 360. So how about we subtract off the 360-degree angle because that's 1 revolution. And what we have left is 180. So that means that 540 is really the same as 180 plus an extra revolution. So we can come back here and we can go to this 180 and say that really if you went all the way around to there, that's 360. And then if you kept going to there, you could put a 540 there. And I guess what we could say is that that 180-degree angle also represents, I'll say or 540 degrees. And on the next page, we've got a 420, a minus 45, minus 180, and minus 300. So we're going to jump to C, and then I'll ask you to pause the video. On part C, it's minus 45 degrees. Okay, minus 45. So I know what positive 45 means. Positive 45 is from here to that one. So negative 45, I guess, must mean the other direction. So negative 45 is the same as this 315. So we can say here, or negative 45 degrees. So real important convention, we start our angles in standard position at the positive x-axis. Positive angles are going counterclockwise. So again, start at the positive x-axis, go counterclockwise for positive angles, clockwise for negative angles. Here in part C, there is another way to do this. Instead of subtracting 360, you could add 360. And if you do that, lo and behold, you get the same 315 that we just landed on. So pause the video, figure out where parts B, D, and E are, and then label them on the unit circle, and then come back. Okay, hopefully we found that this 420 is really the same as 60. If you add 360 to 180, you get positive 180. So going clockwise 180, going counterclockwise 180, they're both exactly the same thing. And then add 360 to this, and we get positive 60. 3, we now extend our definition of the trig functions to non-acute angles. Acute means between 0 and 90. If xy is the point on the unit circle specified by the angle theta, all right, let's pause there for a second. So here's your angle theta. You have this point up here, which is just on the line segment, which is at an angle of theta. Remember we said go counterclockwise from the positive x-axis. So here's theta. You go straight out here until you get to the unit circle. There's the 1, that's the unit. And you land on some point, x comma y, which I guess really means that this thing is your y and this thing is your x. Okay, that makes sense. We define cosine of theta to be x and sine of theta to be y. So whatever the x value is, whatever this distance is, that's what we're going to call cosine of theta. And so you can see cosine of theta is sitting here in the same place as the x is. And whatever sine of theta is, that vertical distance, this distance, that's what we're going to call, or the y is what we're going to call sine of theta. So first, let's make sure this definition agrees with our earlier definition of sine and cosine, which was given by SOHCAHTOA. Okay, so the old definition said that sine of theta is, let's see, OH, opposite over hypotenuse. If we look in this diagram, what's the opposite side to theta? Okay, the opposite side is y, divided by what's the hypotenuse in that triangle? It's a 1. So I guess what we're saying here is that the sine of theta is really the same as y. Does that agree with our new definition? Look, sine of theta is the same as y. And if we played the game but with cosine, SOHCAHTOA says cosine is adjacent over hypotenuse. Which side is the adjacent side for this angle? Theta, it's x. Divided by hypotenuse in that triangle is 1. And lo and behold, the cosine of the angle matches perfectly with the x, which is what we had said here. Cosine is the same as x. Thus, we can label any point on the unit circle as cosine theta, comma, sine theta. That's really important. Cosine theta is always first, sine theta is always second. It's got to be a unit circle. We'll see non-unit circles in a few minutes. Using the unit circle, find the following. Cosine of 180. Okay, so here on the unit circle, cosine of 180. So is cosine the x or the y? Cosine is the x. So we go out here to 180 degrees, which is this one. And our job is just to figure out what the coordinates are of that point. All we care about is the x coordinate. So what is the x coordinate here? Well, it's a unit circle. So the radius is 1 in every direction, but this is an x value and it's left. So the cosine is -1. So this cosine of 180 is -1. So pause the video here, see if you can do B, C, and D. And we'll give you a hint. Your answers are going to be from the collection of numbers 0, 1, and -1. Every answer here is going to be 0 or 1 or -1. So pause and come back when you're done. Okay, let's see how we did. I'm just going to use this circle that's pictured here instead of going back and forth. So 180 degrees is still this angle, still this point. The sine is the y coordinate. And the y coordinate at this point right here, well, this is the point -1, 0. So the y coordinate is 0. So the answer to this one is 0. Cosine of -90. Negative means rotate clockwise. -90 must be there. Here's the point. What are the coordinates of this point? Let's see. It's a 0, and then it's down 1. So -1 there. And is cosine the x or the y? Cosine is always, always, always the x. So this is really asking you for the x. The x is 0. So in this case, the answer is 0. Okay, sine of -630. So -630 must be some nice angle, but it's in disguise. So what if we add 360 to this number? Okay, if you add 360, it's still going to be negative. So how about we add 2 360s or 720? That will be our way to get something that's positive. So add 720 to that. Oh, 90 degrees. Isn't that nice? So this is really exactly the same as the sine of 90 degrees. And the sine of 90 we can find. 90 degrees is at the top. So we're looking for this point up here. Coordinates are 0 and 1. Sine is always the y value, which is 1. So the answer here must be 1. Number 5. Symmetry can help us answer some questions. Find an angle between 0 and 360 that has the same cosine as 320, sine as 320. Okay, so I'll keep using this picture that's up here. So first thing to do is find 320 degrees. So 320 is someplace down here, I guess, right? Because let's see, that's 90, 180, 270, and then like a little bit more. So maybe 320 is in there somewhere. Okay, and so 320 lands you here, and there's some x and y, and we know that it's always cosine first. If it helps, x and y are in alphabetical order when we write them as an ordered pair. Cosine and sine are also in alphabetical order. C comes before S. Okay, so I want another angle that has the same exact cosine as this one. So I need another point on this circle with the same x coordinate as this point. So can we find another point on this circle with the same x coordinate as this point? Well, let's see. If I go straight to the left, I'm going to have the same x that I had, but it's going to be negative. So instead of getting this x, I'm going to get some number over here, which is the negative of that x. But instead of going left, if I go straight up, then this point right here has exactly the same x value, right? Whatever this distance is, that's the x coordinate for this point number 1 and this point number 2. So all I have to do is figure out what angle is represented by this one right here. Whatever that angle is, that's the one that I want. Okay, can we figure this out? Well, let's see. I guess that green angle is the same as this green angle. And I know it's 360 in the whole circle. And if I've already seen 320, then I think that means that this is a 40-degree angle. I guess technically it's negative if you're going clockwise, but I'm just going to leave it as positive 40. So if that's a 40, then by symmetry, it seems like that's a 40. And so our answer here is 40 degrees. That's it. So I'm going to write this as an equation. I'm going to say that cosine of 320, whatever it is, which I don't know what it is, it's got to be exactly the same as cosine of 40. Okay, next one is the same sine as 320. Okay, same idea. We're still focused on this point right here, which is the one that was at our 320-degree angle. But now we want the same sine, which means we want the same y value. So if we decided to go straight up, we would land on some point right here, xy. Is that the same y? Is that the same y as this one? The answer is no. This y is some positive number, and this y is some negative number. So instead of going straight up, we want to go straight to the left. So whatever point we got over here, that's going to be our winner because that's the same y value everywhere on that line. So we just need to find that point. Okay, so here again using symmetry. So we want to think about the fact that 320 is the angle we started with, and we need to figure out what this angle is right here. Okay, well, I guess I like the fact that this angle here in green is 40 because I'm thinking that means this one is also 40. And if that one's 40, then what about the angle that's written here in black? Well, that angle is 180 to there plus another 40 to there, which makes 220 altogether. So then we can write another fact here that the sine of 320 is exactly the same as the sine of 220. Both messy numbers, but they should be exactly the same messy number. Let's check on the calculator. One thing, anytime you're going to hit sine, cosine, or tangent, you got to think about what mode you're in. We'll talk about radians a bunch this semester, but for right now, everything is in degrees. So we're going to type in these two things, cosine of 320 and cosine of 40, and cross our fingers that we get the same number. So cosine of 320 is there, it's messy. Cosine of 40, oh good, same messy number. And then we can do the same thing with the sine. So we'll type in sine of 320, and we'll get some different messy number, but now we want to type in the sine of 220. And we get the same different messy number. Compared to the sine of 40, before I hit enter, maybe make a guess. 40 degrees is this one up here. The sine value, remember, is the y value. So the question is, what is this y value? I'll give you a hint. It's on the calculator screen right now, basically. So that y value up there is exactly the same as this y value, except this one is a negative number, and this one's a positive because it's up there. So it's going to be the same number, but positive. Okay, moving on to number 6. We can approximate other values of sine and cosine using the calculator. We just saw a little bit of that. A, sketch a 100-degree angle on the unit circle and estimate the coordinates of that point. All right, go ahead and pause the video here and come back when you're done. Okay, so hopefully we see that from here to here is 90, and 100 is just a little bit more than that. So let's say roughly that's our 100-degree angle. Maybe not so much, so how about something like that? So that's roughly 100 degrees. And then we're trying to estimate the coordinates of the point. That's the point right up there. So we know that this point up here at the top is 0, 1. It's a unit circle. So what can we say about the x value at this point right here? Well, it's definitely negative, but not very big. So I'm going to estimate that the coordinates of this point are like negative 0.1. It might even be smaller than that, comma. And then the y coordinate, well, it's going to be really close to 1. I mean, it's basically just about at the top of the circle. So maybe it's like 0.95 or something. It's really close to 1. So those are just estimates. B, find the coordinates of that point to the nearest hundredth using your calculator. Okay, so now instead of estimating by just looking at the graph, we're going to recognize that we know that the x and the y are now the cosine of the angle and the sine of the angle. In this case, the angle in both cases is 100 degrees. So this is really cosine of 100, sine of 100. So let's type those numbers in and see how good or bad our estimates were. So cosine of 100, we were hoping something around negative 0.1. Okay, that's pretty good, negative 0.17. And then sine of 100 we thought would be really close to 1, just a hair under 1. 0.98, great. Okay, next, label the point with its coordinates. Okay, so then I guess that I'm just gonna circle this and point. So those are more accurate than the estimates that we made, but I think we did pretty well, so good job. Okay, next page, 7. What about a circle which is not a unit circle? How should we define sine and cosine for a point on a non-unit circle? Well, so in this case we've got our x and y in standard positions, and then we've got the hypotenuse here is now some general r for radius of circle, instead of being a 1. Okay, so let's go back to our SOHCAHTOA days. So we know that sine is the opposite over the hypotenuse. So opposite to theta, what letter is that? That's y. Hypotenuse is r. So we know that the sine is the y divided by the r. I'm going to just cross this off for a second. So sine is y divided by r. Well, I want to know what y is, right? And that's what we're after, is to figure out what y is. So how about we multiply both sides by r? So we get y is equal to r times the sine of theta. So gosh, it seems like that's the only thing that we have. That's the only choice we have. We have to put r times sine of theta. That's what y is. And I'll encourage you to pause the video and play the same game to figure out what goes here. And I will tell you that it's r times cosine of theta. So did we lie before when we said that in a unit circle it was just cosine theta comma sine theta? No, because in a unit circle the radius was 1. So if this is a 1, then you just get cosine theta. And if this is a 1, you just get sine theta. So we were just looking at a special case. In general, it's r cosine theta for the x and r sine theta for the y. 8, let's use this new definition to revisit our Ferris wheel problem. Consider the Ferris wheel pictured below. Its diameter is, and here I'm going to make a change, Same change I made from the last video. I want that diameter to be 20 instead of 24, so please cross it off on your paper. So the new diameter is 20 meters. It's rotating at 3 revolutions per minute, and at its lowest point, it is 5 meters above the ground. Assume the ride starts in the position pictured on the left. So starting is right here. Let's write the height of the car in the picture on the right as a function of the angle theta. So the car initially started here, and then it rotates around to some generic point over there, which is some angle theta away from where we started. And we want to know if we can figure out what the height at that point is. Well, the height changes, right? Initially, the height is 15, and then it's higher, and it's higher still, and at the max, I guess it gets up to, what, 25? Then it starts to get smaller and smaller, the height, smaller, smaller still, until we get a height of 5 at the bottom, and then the height starts to get bigger and bigger until we're back up to where we started. But can we come up with a formula, a function, that will tell me exactly what that height is at any moment? Well, let's temporarily forget about this 5 here, and I'm just going to envision the x and y axes extending this way. So the origin is right there at the center of this circle. So in that case, we can actually use what we found up above to fill in the coordinates of this point. We know that the x is always the r times the cosine of theta. The r, the radius, is 10. So this is definitely 10 cosine of theta. And then the y value is r sine of theta, 10 sine theta. Okay, so which one of those relates to the height? Well, the x gives you this distance here. I'll even label it. So there's the x and there's the y. So the x is the left-right movement, which is important, but not for this problem. This problem is just about the height, and the height is just y. And the y is 10 sine of theta. So I guess what that means is that the distance, the height, from what we're calling the ground, which at the moment is the x-axis, is 10 sine of theta. So then how about we say that the height is definitely 10 times the sine of theta. But that red line is not really where the ground is. The ground is really down here. And so how much distance is there between what we called the ground for convenience and where the actual ground is? Well, that's 15 meters. And it seems like the Ferris wheel is truly, or the car on the Ferris wheel is truly whatever the y is plus another 15. It's 15 more than whatever we found. So it's plus 15. I'll put parentheses here just so we don't think the 15 is inside of that sine function. So that's it, 10 sine of theta plus 15. But wait a minute, you might be saying, what happens when the car makes its way over here, which is like under the ground that we had? Does it still work? Well, let's check. So let's just go ahead and put the car at some arbitrary spot here. And in this case, the height below the ground, let's just make up a number. So maybe that's something like -3. So it's like 3 meters below the ground. If this thing right here is -3, and then you add the 15 to it, we get 12. Would that be right? Would that be the actual height? Would it be 12? Yeah, sure, would be. It would be 12 meters there because the extra part was 3. So I think we're okay. Even when the y coordinate is negative, I think adding 15 is still the right thing to do. And one nice thing we can do to check our work here is to type this function here into the calculator and see what it says. So let's try that now. So we'll go into y equals, and we're going to type in 10 sine. Okay, it's unfortunate we're going to have to use x here because that's the only variable we have on the calculator. It's really a theta that we're thinking of. It's not this x coordinate, so please don't be confused by that. That's theta plus the 15. Now I want to think about a good window before I do anything here. Theta is the x now. So what's the smallest x that makes sense? What's the smallest theta that makes sense? What angle are we at initially is 0. If we want to do one complete revolution and get back to where we started, then we should go to 360 degrees. How about we go by 90s? Those are the nice quarters. And then the y is going to be the height. And the height is bottoms out at 5, tops out at 25. How about we just go 0 to 25? So if we did this right, then we should see one complete revolution. It should start right there in the middle at a height of 15, get up to 25, down to 5, and then back. Starts in the middle, up to 25, back through the middle, down to 5, not to the axis, and then exactly right back to the middle. One complete revolution. Number 9 is the activity, so I'll make a separate video for that, but before you check the answer, oh, I don't see an answer. So before you check the video, give this a shot and then you can take a look at the video.